recording which is focused purely on my screen, and another which is capturing my video as I'm walking and I can gesticulating and drawing things, etc. And we're using them in a sort of fail-safe way to ensure that I have reliable recording of decent quality for the boot camp. And so far it seems to be working pretty well. Catching things that fall through the cracks. Okay, so ladies and gentlemen, this model is one that we crafted yesterday, and I just want to remind you of it. This model has within it, has within it the SAR model we've just been discussing, which has income linked crowding and transmission of an illness. But we noted yesterday that there was a lot of variation from run to run. And in order to understand the regularities behind that variation, we created what's called a parameter variation experiment. Now, our primary uses of that for most of yesterday morning centered specifically around the summary of many runs of the model. So we went to the parameter variation experiment and we ran it a certain number of times in what's called free-form mode with fixed values of parameters. And we saw and we summarized those runs using what's called a 2D histogram, which basically counted the number of times that runs fell within a small grid item here, where, for example, for a certain time, say time 200, how many of the runs had 30 people infected, or 31, or 32, 33, etc. So if you were to cut this vertically and look at it from the side, you'd see a histogram. There'd be a histogram, and the darkness of the line would indicate the number of counts that fell in that histogram bin. So here there are no runs where we had 0 to 1 or 1 to 2, etc. But then once we started getting up to about 20, there were a few runs that had it. Once we were about 30, there were more runs. And then once we got to about 32, it went way down again very quickly. And it was just about 0 all the way up. So if we were to look at this from the side, we'd see a histogram coming up and going down. And it's a 2D histogram because we're also grouping things by time. We're asking time 100 to 105 or what have you, how many fell within that range. And this gave us a sense of some regularities. We saw that these first bunch of oscillations are pretty regular, despite the stochastics, whereas this later wandering is quite heavily stochastic, and the exact timing of the peaks and so on are subject to the vagaries of the stochastics, and therefore it didn't have a lot of regularity about the exact timing. Interestingly, there were, and this will come back in our discussion of calibration, there were some features of that later time that are very regular. The fact that there are oscillations occurring there is quite consistent across runs of the model, but the exact timing, when exactly they crest and wane, that varied from run to run. And that's something we'll want to think about when it comes to calibration. I'll make some remarks more broadly about calibration to get us out of the idea that it's always about point matching, okay? Okay, so this sort of graph kept us honest in a way about the significance of a particular run by reminding us that we can't overinterpret the exact timing of of items, after about time 150, that it's highly variable, whereas those before are significant regularities that we can expect to see. But a graph like this didn't really alert us to the fact that as to how much this would change as we change parameter values. And after lunch, I started to talk about that some in a little bit more detail, talking about how if we varied these in ranges, for example, if we said here that we would change the mean duration of immunity within a certain range, exploring as it went from, you may remember its fixed value is 30. So if we were to say, let's make it from 10 to 50 with a step value of 2, we could then simulate the model in response to that so-called one-way sensitivity analysis. Here, we're systematically varying in a fixed arithmetic fashion the value of this parameter and examining the outcomes. So here it would go from 10 to 12 to 14 to 16. And you'll notice when we do this, we selected varied in range, and we could no longer specify the number of runs. It's a little bit confusing because 100 still shows up there, but you notice that it's as we say, disabled. It's grayed out here, a number of runs. That's an indication it's not paying attention to that. The number of runs is purely given by this range. Okay, so here we're going from 10 to 50 by a step size of 2. And that implies, inevitably, that we're going to have a specific number of runs. If you think about it, if you go from 10 to 12 by a step size of 2, you'll have two runs. It's 12 minus 10 divided by 2 plus 1. So here we have 50 minus 10 divided by 2, because we're doing it in steps of 2. So that's 40 divided by 2, 20. And then plus 1, because we do it to include the end one, 50 itself. And so we should see 21 runs of this. And if we go and we were to do that here, we're to do run here and execute. The food is here?
The food has arrived, but I also have a couple other things we need to take care of.
Oh, okay. Okay, great. So I'll just finish up. Okay, great. So here we go, ladies and gentlemen. We see for successive values of this, the induced behavior, okay? The behavior that comes about. What you may have noticed is, not surprisingly, for smaller values of duration of immunity, it started up here from higher numbers of people infected, and then as we posited larger and larger durations of immunity, we got lower and lower numbers of individuals infected at these times, reflecting the fact that fewer people are in play can be infected because they're not susceptible. They're in this recovering state where they maintain their immunity. So here we see as we change the value of a parameter, how the behavior of the model is different. We also saw yesterday after lunch that we could do this in 2 additional ways, which was fruitful. One way was to examine several changes at once. So for example, asking about as we change the mean recovery time in parallel with the duration of immunity, and we stepped each of them, we could consider all possible pairs of those in turn. And that allows us to examine not just how the responses of the model varies with one in isolation, which is very helpful for understanding how sensitive it is to this assumption, and by implication, how much effort it might be worth putting into determining this. But here we're doing it with 2, because the impact of mean duration of immunity the significance of changing the value of that parameter might be quite different depending on our assumptions of this earlier parameter. If we change this earlier parameter, mean recovery time, so it's so short that almost no one is getting affected, then presumably changing the duration of immunity has comparatively little impact, because no one's getting infected. It doesn't matter how long. If they were infected, they stay immune. It's a moot point. And as a result, we can see these interaction effects of these two parameters in a sort of exhaustive fashion. Now, that would be called the multi-way sensitivity analysis, and it's one way we talked about yesterday. The other way being what's called Monte Carlo sensitivity analysis, where we're actually drawing these values from distributions. We're going to talk a little bit more about that after this, after the break, and after a distribution of a combination of marks of appreciation, but also medals of honor. We will reconvene after this break.
I need to know who has the passcode that ends in 107 and 113.